Okay, I'm working on section 7.1, doing the first problem here. Going to work through these odds up through about 19 or so. So on problem number 1, they actually give you a graph of two functions. Draw a real rough picture of this. They give you that this is the point 4,4, and they give you that this is y equals x, and that this parabola is y equals 5x minus x squared, and we're trying to find the area of this region. So first of all, we notice that these are both functions of x because they are solved for y. You have y isolated, so this is a function of x. I'm going to call this one f of x because it's the function that's on top here. And then this one over here, I'll call this one g of x, since this is the one that's on the bottom of the region. And so we imagine that we can construct a rectangle in this region, and that rectangle, we're going to take an infinite number of them and add them up. So that rectangle has a height. See, if this is the x-axis, the height of this rectangle is the top of it, which is the f function, and then the g function is the bottom. So that means that this distance is f of x minus g of x. And so the height of this rectangle is f of x minus g of x. And then the width of the rectangle is going to be our dx. And so when we set up our integral, this inside is the area of that rectangle, which we said was f of x minus g of x. That's the height of the rectangle, then times its width, dx. And then we need to add all of them up, an infinite number of them, so that's where the integral comes from. And we have to find our limits of integration. And since we're integrating with respect to x, we're looking for x values. So you can see that this region starts at an x value of 0, and this region stops at an x value of 4, and that's given to us right here by that 4. So I'm ready to write up this integral. And I think for all these problems, I'm not going to work out the actual integration. I'm just going to set up the formulas and let you do the rest. So we'll have the integral from 0 to 4 of f of x, which was the top function, which was the parabola. That's 5x minus x squared. And if you want, you could put it like this. That's f of x. Minus g of x. G of x was just y equals x. And then dx. Make sure I've got that right. Yes. I'll go a little bit further. I'll actually do the integration, but I'm not going to plug in the numbers. So we'll have integral 0 to 4. This is just 5x minus x squared minus x. When you distribute that through, there's really only one thing to do, and that's just make it a negative. But if I had multiple terms here, that negative would have to go through both terms. I can go a little bit further. Integral 0 to 4. 5x take away x, that's 4x minus x squared dx. And then, of course, if I take that and integrate it, I'm going to get the antiderivative of 4x, which is 2x squared. Then the antiderivative of negative x squared is negative 1/3 x cubed, evaluating 0 and 4. So I plug 4 in, I get a number, plug 0 in, get a number, subtract, and that's my final answer. That represents the area of that region. All right, so that's number 1. Let's look at number 3. So with 3, again, they give you a picture. And they tell you that this curve right here is x equals e to the y. And they give you this parabola looking thing. Opens sideways, goes like that. and they tell you that this is x equals y squared minus 2. Then they give you these two lines like this. And they tell you here y is equal to 1, and down here this one y is equal to -1. What we're trying to do is find the region, the area, sorry, of the region here, which is what they shade that for you in the problem. So on this problem, what we realize is that if we try and do vertical rectangles, things aren't going to work out, because if we try a vertical rectangle right here, then the top function and the bottom function are actually the same curve. And so that curve fails the vertical line test. It fails to be a function of x. Anytime we're dealing with things that are not functions of x, instead functions of y, then what we want to do is we want to just rotate our rectangle, make it a horizontal rectangle instead, like this. And then notice that the curve that's going to create the right side of the triangle, this one, is always going to be the right side, triangle, right side of our rectangle, is always going to be the right side of the rectangle. No matter where we move that rectangle, this blue curve is always the right side of it. And then the left side of it is always going to be the other curve, which is that parabola looking thing. So I'm gonna have to look at these as functions of y instead of x. I'm gonna call this one right here, the blue one, I'm gonna call this one f of y, because it's the one on the right side. And then I'm gonna call the red one over there, which is this one right here, I'm going to call that g of y. And so we have the same exact principle that we did before. If we want to find the area of this rectangle, it's going to be the width of it, which is f of y minus g of y, and then the height of it, which is dy instead of dx. Because our shift, when we move that rectangle up and down, it's the y value that's changing. So a rectangle looks like this. This is dy. This side is f of y minus g of y. And so our integral is going to have f of y minus g of y. So f of y is e to the y. Since there's only one term, I'm not going to put in parentheses. Minus g of y, but that's two terms, so I am going to put that in parentheses. Okay, so that's f of y minus g of y, and then dy. Now I just need to figure out what I'm integrating from. And so since I'm integrating with respect to y, I'm looking at where this region starts and stops in terms of the y values. And they actually give that to us. They say start at y equals -1 and at y equals 1. So I'm just going to go from -1 to 1. And that's it. Now we just need to clean that up and integrate, and we're done. Again, I'm not going to plug in the numbers at the end. I'm just going to do the integration. So I'll first distribute the negative through. So e to the y minus y squared plus 2 dy. Now I go ahead and take the antiderivative. Antiderivative of e to the y is itself. Antiderivative of negative y squared is negative 1/3 y cubed. Antiderivative of 2 is 2y. And I'm going from -1 to 1. And then I go ahead and plug in and do my subtraction. All right, that's 3, 5. So 5 is the first one where they don't actually give you the curve, so we're going to have to be able to draw it. So y equals e to the x, y equals x squared minus 1, x equals -1, x equals 1. So I'm supposed to sketch this region and find the area of the region. So sketch the region bounded by those curves and then sketch it. Sketch it and then find the area. All right, so let me start out with my picture. It appears to me by looking at it, since these two are solved for y, that these are both functions of x. So I'm already thinking this is probably going to be vertical rectangles, but I need to get the picture drawn first. So y equals e to the x. I'll do that in red. Y equals e to the x. I mean, it looks like this. Okay, that's y equals e to the x. And then the other one is y equals x squared minus 1. This is a parabola like this, but it's moved down 1. So just shift it down 1. It looks like this. And it goes like that. Goes like that. And then we have x equals 1 and x equals negative 1. These are vertical lines. So x equals 1. Let's see, where would we be? If I plug 1 in to this, I get 0. So I know that hits there. So I have y equals 1. I mean, sorry, x equals 1. That looks like this. X equals 1. And I forgot to label the blue one here was y equals x squared minus 1. And then x equals negative 1 is there, and that goes like this also. So the region bounded by all of the curves is this region in here. And you can see that if I draw a vertical rectangle, then the curve that's on top is the red curve. The curve that's on the bottom is the blue curve. And that's always the case. If I move this left and right, that's always the case. So my top function is the red one, e to the x. My bottom function is the blue function, which is x squared minus 1. So I know that the height of the rectangle is this minus this, and the width is going to be dx. So the question becomes, where am I going to integrate from? So where does this region start at, what x value to start at and stop at? I forgot to label this x equals negative 1. Starts at x equals negative 1, ends at x equals 1. So I'll set that up. Integral x equals negative 1 to 1. And then the top function, which was e to the x, minus, and then the bottom function had 2 terms in it, x squared minus 1, so I'll put it in parentheses, dx. Distribute the negative, e to the x minus x squared plus 1 dx. And now I'll go ahead and integrate this. So antiderivative e to the x is itself. Antiderivative of negative x squared is negative 1/3 x cubed. Antiderivative of 1 is x. I evaluate negative 1 to 1. So plug in 1, figure out what you get, and then plug in negative 1, figure out what you get, subtract the 2, and you're done. So part of this problem is, just getting the picture. And, I would encourage you to use your graphing calculator to assist you. But with functions like the ones I just gave you, there's really the expectations that you do know how to graph simple polynomials and exponential and quadratic functions. All right, number 7. All right, it gives you y equals x minus 2 squared, y equals x. And that's all they give you. So we're going to find the region bounded by these two. We're going to sketch it. We're going to find the integral that represents its area. So x minus 2 squared. This is a parabola. And if you remember back from college algebra, if you have a parabola in what's called standard form, then the h and the k tell you where the vertex of this parabola is. So when you look at this right here, we actually have 1 x minus 2 squared plus 0. That's what this is. And so this is just a parabola that's been shifted so that the vertex is at positive 2. You can check it. If you plug positive 2 in here, you get 0. So we know that when we go out to 2, we get 0. 1, 2, we're at 0. And then it opens up like this. Okay, and then y equals x is just the diagonal. So that looks like this. Like that. I'll extend this one a little bit. So the region that we want is in here. And I hope that you can see that, again, vertical rectangles are what's going to work here. These are both functions of x because they're solved for y. But more importantly, if you draw an arbitrary rectangle in this region vertically, you can tell that with that rectangle, the function on top, which I'll say is this blue line, right, here, well, and then you have the function on the bottom, which is the parabola, here, this piece, that as you move this rectangle left and right, the blue on top and the red on the bottom never change. It's always those two functions. So my top function is y equals x, so just x. The bottom function is the parabola, which is x minus 2 squared. So I know in my integral already, I'm going to have the top function x minus the bottom function, x minus 2 squared dx. I just need to now resolve where this region starts and stops. So it starts here, some x value down here, and it stops here, which is some x value down here. I've got to figure those out. And in the previous problems, those were kind of given to us. So in order to figure out the intersections, what we do for the intersections of those two graphs is we set the two curves equal to each other. I want to know when this x function is equal to the x minus 2 squared function. So I just write that down. When is x equal to x minus 2 squared? And then what I'll do is I'll expand the right side, so I'll FOIL that out, and I get x squared minus 4x plus 4. And then I'll realize I have a quadratic equation, so I'll move everything to one side. So 0 equals x squared minus 5x plus 4. And then I can also factor the right side, x minus 4, x minus 1. And that gives me two solutions. The solutions are 4 and 1. And so I think you can tell by looking, my graph is decent, that these hit each other at 1. So maybe I just move that over, 1. And then over here they hit at 4. And so that gives me my limits of integration, 1 and 4. So now I need to integrate this. And you have a couple of different options on how to integrate that. What I would do, if I were doing this problem, I would just expand out this. So I have integral 1 to 4. I'd have x minus, now be real careful here. When I expand this out, I get x squared minus 4x plus 4, right? But I have that minus sign in front. So that minus would need to go through to all of these. Integral 1 to 4, x minus x squared plus 4x minus 4 dx. And then I can collect some like terms together here. So this is equal to integral 1 to 4. Let's see, I'll put it in descending order. Negative x squared. See, x and 4x is 5x. And then minus 4 dx. And then from there I integrate. I get negative 1/3 x cubed plus 5 halves x squared minus 4x. Evaluating 1, 4. So plug in 4, figure it out. Plug in 1, figure it out. Subtract, you're done. All right. Take a quick little break. There it goes. Okay, so working on number 9. So right away, I noticed that these are functions of y because they're solved for x. So I'm thinking I'm going to have horizontal rectangles instead of vertical rectangles. But let me just do the graph and see how this works out. Now, in order to graph this, I can do it a couple of ways. I can realize that it's a parabola that opens to the left and it's been moved to the right one. Okay, but that would depend on my background, I guess. So if you have trouble with this, you do first of all need to know it's a parabola, okay, because of the y squared. It's just that it opens left and right instead of up and down. And then you could plug in some points. So like if y is 0, x is 1. So that means if my y coordinate is 0, my x coordinate is 1. That means I have a point here. If y is 1, which means I'm up here, then the x value here is 0. So I'd actually be here. If y is -1, then again, when I square it, I get 0 here, so I'll be here. And I hope that that's enough for you to see that parabola opening up like this. So this is x equals 1 minus y squared. Then we have another parabola. I'll do it in a different color. I'll do it in red. This one, if you plug in 0 for y, you get -1 for x. So you're here instead. 0 for y is right here. -1 for x is here. If I plug in 1 for y, I get 0 for x. So 1 for y, I get 0 left and right, so I'm here. And if I plug in -1 for y, I also get 0, which puts me here. And this parabola opens this way. So the region is pretty clear that it's right in here. And if I come in here, I'm going to change this one to a blue one. I notice that if I try and draw a vertical rectangle, that the top function and bottom function are the same curve, and again, I can't do that. But if I go sideways, horizontally, if I draw a rectangle in here, then that rectangle is going to have, as its right boundary, the blue curve, and as its left boundary, it'll have that red curve. And that'll be the same no matter where I move that rectangle in that region. So that means I want to integrate with respect to y. And then I'll want to take the function on the right minus the function on the left. So the right function was this blue one. I forgot to label it. X equals y squared minus 1. So this is going to be y squared minus 1. And then this red one on the left is this one. Did I get that? No, hold on. Mislabeled, sorry. The red one is x equals y squared minus 1. And this blue one up here was this one. X equals 1 minus y squared. So the blue one, 1 minus y squared. The red one is y squared minus 1. So I'm ready to set up an integral. I'm also going to need to know when my y values start and stop. And that's pretty easy to see that from the intersection. You don't need to actually go do the work for it. It starts at y equals -1 and stops at y equals 1. So these are my bounds. The bounds are on y, -1 to 1. It's going to be the right function, which was the 1 minus y squared, minus the left function, which was y squared minus 1. And then I'm integrating with respect to y. And so this equals integral -1 to 1. Let's see, I can drop the parentheses here. Here I distribute. So I get 1 minus y squared plus 1 dy, which gives me integral from -1 to 1. Let's see, I've got negative y squared, so forgot the 2. -2y squared, and then I have 1 plus 1 is 2 dy. And that's it, ready to integrate that. So the antiderivative of this is going to be -2/3 y cubed plus 2y Antiderivative of 2 is 2y. Negative 1, 1. Do your subtraction, and you're done. Okay, next one. Where are we at? Number 11. Y equals 12 minus x squared. Y equals x squared minus 6. All right, so we've got to graph these first. These are both functions of x. Since they're functions of x, I know I'm going to probably use vertical rectangles, but let me graph them. This one, parabola, opens down because of the negative, and it's moved up 12. So you could also write it like this. So parabola opens down, move it up 12. So way up here at 12, I have this parabola. I may as well draw it in blue now. It goes like this. And then I have another parabola which opens up because there's a positive in front of the x squared, and it's moved down 6. So if that's 12, down 6 is like this, negative 6, and this guy does something like this. And the region that we want is the region bounded by both, which is in here. You can see that vertical rectangle is going to work out perfect here. My vertical rectangle will always have as its upper bound the blue function, which is the one up here. And on the bottom will be the red function. Let's see, the blue function is the parabola that opens down, which was 12 minus x squared. And as the bottom, it'll be the parabola that opens up, which is x squared minus 6. And as I move that rectangle from left to right, it will always be that case. So I am ready to set up my integral. Also need to figure out the starting and stopping point. So I do need to figure this out, what x values these hit each other at. So I guess I'll do that now. I need to figure out the intersection. So I'm going to set the two curves equal to each other. 12 minus x squared equal to x squared minus 6. And I'll move everything over to one side. How about I move everything to the right? I've got 0. Move this over, I get 2x squared. Move this over, I get minus 18. And so if I pull out a 2, I get x squared minus 9. That's a difference of squares, so x plus 3, x minus 3. And so I set all these equal to 0. The 2 doesn't matter. I get x's negative 3 and positive 3. And so this should be negative 3. This should be positive 3. So it's integral time. My integral is going to go from negative 3 to 3. It'll be the top function minus the bottom. The top function was 12 minus x squared. The bottom function was x squared minus 6. And this is integrating with respect to x, because I've got vertical rectangle, and that's because I had functions of x. So now we come in here. This is integral negative 3 to 3 of 12x minus x squared plus 6 dx, just distributing through. And let's collect our like terms together. We've got negative 2x squared plus 18 dx. And antiderivative time, negative 2/3 x cubed plus 18x, negative 3. Plug in, subtract, you're done. I'm trying to do this while I eat because I'm really hungry right now. multitasking. All right, moving on to 13. Oh, okay. Y equals e to the x. Y equals x e to the x. Then x equals 0. All right, so let's see if we can graph this. This is going to be kind of interesting. Y equals e to the x. Start with that one. Okay. Now, x e to the x. That may not be something as obvious. So let's just plug in some points. If we plug, well, you know what? Before we do that one, x equals 0. Where is x equals 0? X equals 0 is a vertical line. And it's actually the y-axis. So that's x equals 0. So let's just keep that in mind, that the picture that we're going to look at is going to have to be bounded by all of these. So when I draw my next curve, just keep that in mind. That green one is going to create part of the region. So now x e to the x. If I plug in 0 for this, for x, I get 0 times e to the 0. That's 0 times 1. That's 0. So I know at 0, I'm at 0. If I plug in 1, I get e to the 1, right? 1 times e to the 1. 1 times e to the 1 is equal to e to the 1. So what should happen is at 1, I should be at e to the 1, but that's actually right here. And the reason why it's right there is because on the red curve, if I plug in 1, I also get e to the 1. So at 1, both of these functions are the same, the red one and the blue one. Now, the question to me would be, what's happening between here? So like, what if you did like 1/2? So we know that if I plug in 1/2 to this, I get 1/2 e to the 1/2. So what would happen if I plug in 1/2 into the red one? I would get e to the 1/2. So at 1/2, the red one's up here at e to the 1/2. At the blue one, we're half of that. So we're half as high, which means my graph is right here somewhere. And that's going to be the same case the rest of the way through in between here and here. So I know that this curve is going to go below that one and then go up to there. And what happens after that, I'm not sure, but I can see that the region's already been created. It's right in here. And then you could see your vertical rectangle right there. Blue one's on the bottom, red one's on the top. Red one is e to the x. Blue one is x e to the x. And so we should be in business. It'll be the integral of the top one minus the bottom one. We do need to know where it starts and stops. So it starts here at 0 and it stops here at 1. So I don't necessarily need to figure out the intersection point, but I'll just show you real quick how you would do that if you had to set those two equal to each other. If you set e to the x equal to x e to the x, what you would do is not divide both sides by e to the x. You'd move this one over to the other side. You'd factor out e to the x. You set these both equal to 0. E to the x can never be equal to 0, so we're not worried about that. But this one, set to 0, you get x equals 1, which corresponds to that point right there. So that's more of an FYI thing. All right, my integral goes from 0 to 1. It's the top function, e to the x, minus the bottom function, x e to the x, dx. So we now need to integrate this, and we can integrate the first one pretty easily. The antiderivative of e to the x is itself, but the antiderivative of x e to the x is not as simple. So watch how I do this. I'm going to break this up into two integrals. This one right here is just e to the x evaluated 0, 1. Then minus So I would have to go through and have to plug in 1, plug in 0, get an answer here. Subtract from that whatever this is. Now, this integral x e to the x, I'm going to do on the side here is scratch work. I've got to figure out what the antiderivative of x e to the x is. And for that, I'm going to use integration by parts. I'm going to let u be x, dv be e to the x, dx. It means v is e to the x, and that means du is dx. So this equals, by integration by parts, that equals ultraviolet x e to the x minus integral voodoo v du is e to the x dx. And that's equal to, see, we can do this integral now, so that's nice. That's equal to x e to the x minus e to the x. So antiderivative e to the x is itself. So that's what the antiderivative of this thing is. So when I come over here, I put that antiderivative down right here. X e to the x minus e to the x. And I'm evaluating that 0, 1. So this integral we could do, no problems, minus, because there was a minus here. This integral became that, and now we can go through and plug in and figure an answer. I'll go ahead and do this one. I'm going to do it the whole way. So this equals, let's figure out what this is first. All right, and I'll do it in blue. So that equals, let's see, something minus something. Plug in 1, e to the 1. Plug in 0, e to the 0. And then I have minus, because of this. And then I'm going to have two things, so I'll be real careful here. It's minus whatever this turns out to be. So minus whatever that turns out to be, and that has two things in it. So notice my parentheses and stuff. I have that minus hanging out here. If I plug in 1 into this, I get 1 e to the 1, 1 times e to the 1 minus e to the 1. That's what I get when I plug in 1 here. When I plug in 0, I get 0 times e to the 0 minus e to the 0. So let's figure out what these are. So this equals e to the 1 is e, minus e to the 0 is 1, minus, in brackets, okay, this is e to the 1 minus e to the 1, that's a 0, minus 0 times anything is 0, that's gone, and then minus e to the 0 is 1, so minus 1. So I have the 0 here, minus, and then in here I have minus 1. So we get e minus 1. Let's see, these two together is plus 1, but then minus 1. So you get e minus 2. That's it. What number was that? Forgot. It's number 13. Just going to look in the back here, check this one. All right, 15. X equals 2y squared. So I'm already thinking horizontal rectangles because it's a function of y. X equals 4 plus y squared. Yep, I'm thinking horizontal rectangles. Got to be able to graph these. All right, let's start with this one. If y is 0, x is 0. I'll do that one as blue. If y is 0, x is 0. If y is 1, x is 2. So if you plug in 1 for y, square it, you get 2 times that. So if y is 1, x is 2 here. If y is negative 1, same thing happens. x is 2, and of course this is also a parabola because it's x equals something y squared. And then for the next one, it's also a parabola. So let's see what happens. If y is 0, x is 4. So if y is 0, x is 4, here's 4. Y is 0, x is 4. So here. Now let's see what happens. If y is 1, so if y is 1, then you square it, you get x is 5, which is 4 out here, 5 like this. And then same thing happens at -1. And so what you have here is a parabola opening up like this. So if I extend the blue one out, what I'm kind of hoping for is that the blue and red ones will hit each other somewhere. I'm gonna have to figure out where that happens. Somewhere around here and here, somewhere they should hit each other. And in my region, definitely don't want vertical rectangles. A horizontal rectangle will work out perfectly. Take that horizontal rectangle like that. I'm going to have the blue curve on the bottom, the red curve on the top. See, the red curve was 4 plus y squared. The blue curve was 2y squared. So I already know how I'm going to set up my integral. I just need my limits of integration. So I need to figure out where these y values are that they hit each other. So to do that, I have to set these two equal to each other. So for the intersections, I set 2y squared equal to 4 plus y squared. I'll move everything to one side. So if I subtract y squared, I get y squared minus 4 equals 0. And that y plus 2, y minus 2 equals 0. So your two answers are, you set those equal 0, you get, it's way down here, it's at -2, that's where they hit each other, okay, out here. And at +2, way out here somewhere, that's where they hit each other. So my drawing's a little off, but you can tell what's happening here. All right, so now I can set up my integral. Should be able to do that right here. Integral, the y value starts at -2, stops at 2. And then it's the function on the right side, 4 plus y squared, minus the function on the left side, which is just 2y squared. I didn't need the parentheses on the 2y squared, but I may as well. Clean it up. Integral -2 to 2. Let's see, we have 4 plus y squared minus 2y squared is minus y squared dy. And then you can go ahead and integrate. You get 4y minus 1/3 y cubed, -2, 2, and then you figure out what that is. Okay, moving right along here. What am I on? 17 cosine pi x. Ooh, this one looks nasty. Number 17. Y equals cosine pi x and y equals 4x squared minus 1. Yeah, this graph is going to be weird. So let's see here. See what I can do with this. All right, let me start with this because it's a quadratic. I know it opens up and it's been moved down 1. So let's see. Try and get a pretty decent graph of this. I know it starts here. When I plug in when I plug in 0 for x, I got that for y. If I plug in 1 for x, I'm going to get 3 for y. So at an x value of 1, I'm up here at 3 for y. 1, 2, 3. So I'm up there. If I plug in -1, the same thing happens. So I'm here. So I've got some parabola that does something like this. Okay, that's y equals 4x squared minus 1. Then I have cosine of pi x. Uh-oh. Hold on a second. Okay, so I'm going to have to stop in a second, but what's my time? Oh, good, it might work out. So cosine of pi x. So let me start with 0. If I plug in 0 in for this, I get 0 for the whole thing. Cosine of 0 is 1, so I know that I'm here. And then, if I plug in, let's say, what do we want to do? Let's plug in x equals 1/2 into that. Because if I plug in 1/2 in here, I get cosine of pi times 1/2 is pi over 2. Cosine of pi over 2 is 0. So at 1/2, which is here, I'm at 0. And then if I plug in -1/2, I get the same thing. So I know that my cosine function goes down like this and then does something like that, and it's going to do the same thing on the other side. And it looks like I can kind of see what the region's going to be. It's going to be this region in between these. This is not a good picture. Here we go. Like this. Okay. My cosine would do that. So I'm thinking it's this region in here, right? Like that, vertical rectangles, which if I do that, the function on top's the blue function, that's the cosine pi x. But the red one, I'm sorry, yeah, I haven't drawn it in red yet. The red, which is the bottom part here, that will always be on the bottom, and that's the 4x squared minus 1. But to figure out where these hit each other, like I really don't know where those hit each other at all right now. I'm going to have to try and find the intersection points. And that is going to, initially, it's going to look very intimidating, all right? Because check this out. If I find the intersection points, I've set these two equal to each other. So for the intersection, I set cosine pi x equal to 4x squared minus 1. And to solve this, this would be a real pain in the butt because you can't get x isolated easily because the x is trapped in the cosine. So you try and get it out of there, you come in maybe with arc cosine, but then the x is trapped inside the arc cosine. There's no simple algebraic way to do this. So our only hope is that we actually can guess at it. And I'm thinking the picture might be leading us to this. We knew that when we plugged in 1/2, the blue function hit the x-axis. What would happen if we plug 1/2 into this one? Notice what happens if you square a half. You get a fourth, 1/4. 4 times a fourth is 1. 1 minus 1 is 0. So amazingly, because they picked the problem to make sure that it worked out nice for you, that if I take this and I plug in a half, I get that, which is 1 minus 1, which is 0. So if I plug a half into this, I get 0. But we saw earlier that if I plug a half into the other one, we get cosine of pi over 2, which is also 0. So just by looking at this, the solution to this is x equals 1/2. But it also worked on the other side. If you plug negative 1/2 in, it would change that to a negative 1/2. It would square it. It would still be the same thing. And cosine, of course, cosine is an even function, so plugging in -1/2 and +1/2 will give us the same thing. So we actually have two solutions, -1/2 and +1/2. What do you think about that? Well, I think I told you in class, sometimes it's just almost like a wild guess. I don't know if you would say that that was a wild guess. That was more of an educated guess. All right, so I know that the integral starts at -1/2, stops at 1/2, and I know it's the top function, cosine pi x, minus the bottom function, which is 4x squared minus 1 dx. I put the 4x squared minus 1 in parentheses. All right, I'll go ahead and integrate this. Well, let me distribute that negative sign through first. This is just cosine pi x minus 4x squared plus 1. I'm expecting a student to knock at the door any second now. And then I'll take the antiderivative. Antiderivative of cosine of pi x is 1 over pi. Have to scale it because pi is like a constant. Sine pi x. And then minus 4/3 x cubed plus x evaluated -1/2, 1/2. And then you have to plug in, which would probably be a little bit of a pain. Should I do this one? Yeah, I'm not going to be able to start another one. I'll do this one until that student shows up. Okay, so let me first plug in 1/2, then -1/2. So if I plug in 1/2, 1/2 right here, I get pi over 2. Sine of pi over 2 is 1. So I'm going to get 1 over pi times 1, which is just 1 over pi, minus, now what happens when I plug in a half into here? 1/2 times 1/2 times 1/2 is 1/8. So I have -4/3 times 1/8. And you can reduce out here, you get -1/6. Yes. So -1/6. And then if I plug in 1/2 right here, I get 1/2. Let's see what that is. All right, so now we plug in -1/2. If I plug that in, I get -1/2 times pi is -pi over 2, which is down here on the unit circle. Sine of -pi over 2 is -1. So this is -1 and then times 1 over pi. So I get -1 over pi. And then if I plug in -1/2 into this, it's the same thing as this, but it's -1/8, which makes it +1/6. So +1/6. And if I plug in -1/2 right there, I get -1/2. All right. This is 1 over pi minus 1/6 plus 1/2. Distribute the negative through. Plus 1 over pi minus 1/6 plus 1/2. All right, nothing cancels here. All right, well, if you have 1 over pi plus another 1 over pi, that means you have two 1 over pi's, so that's 2 over pi. -1/6 minus 1/6 is -2/6, which is -1/3. And then 1/2 plus 1/2 is 1. And we can put these two together. That gives us 2/3. So 2 over pi plus 2/3. And I'm wondering if maybe the book gets a common denominator or something like that. Let's see. What number was this? No, they just leave it like that. 2 over pi plus 2/3. So that's good enough. Interesting problem. All right, that's it for my video. I'll get another one to finish this up.